You think you know Mars. Small, cold, red, done. You've seen the same textbook picture your whole life. A dead desert waiting for astronauts and nothing more. But that version of Mars is wrong in ways that are going to feel very uncomfortable once you see the actual data. In this video, we're going to walk through the evidence step by step and flip your mental image of the planet completely until Dead World stops making sense and you start to realize Mars has been playing a much quieter, much stranger game this entire time. So why do people still call it dead if all of this is going on? A big reason is how you think about time. When you hear 1 million years ago, your brain files that under so long ago it doesn't matter. It feels like another universe. But for a planet, 1 million years is recent. Mars is 4.5 billion years old. 1 million years is less than 1/4% of its lifetime. If a lava flow on Mars is only a few 100,000 years old geologically, that is recent activity. On Earth, volcanologists usually call a volcano active if it has erupted in the last 10,000 years. Mars is smaller and cooler, so its heartbeat is slower. But the logic is the same. If it did something geologically recently, it can do something again. So what are the main pieces of evidence that Mars is still active? Not just long ago, but in the present era. You can group them into 4 big clues that show up again and again in the data. First, Mars's quakes. The InSight lander recorded hundreds of marsquakes over about 4 years, including events around magnitude 4 to 4.7. That only happens if the crust is still under stress and the interior is still adjusting. Second, there are volcanic deposits in regions like Elysium Planitia that look geologically young, with crater counts suggesting ages in the tens of thousands to a couple 100,000 years. Third, the dunes and dust sheets across the surface are actually moving on human timescales, with dune crests shifting by roughly a metre over a Martian year, about 1.9 Earth years. Fourth, the polar caps are not just sitting there, they are actively freezing and sublimating carbon dioxide, which makes the air pressure swing by roughly 25 to 30% every Martian year. Add the ongoing atmospheric escape, a few kilograms of gas per second, and you're not looking at a frozen picture, you're looking at a system still changing. If those 4 clues are real, what does that mean for someone who will actually go there, not just watch a documentary from far away? It means all this background activity turns into direct, practical problems you have to design around. Marsquakes mean the ground under your base is not perfectly stable, especially near active fracture zones, so you don't treat it like some ancient solid block. You need structures that can flex a bit. You avoid building right below steep cliffs. You think about how regolith shielding might shift if the ground shakes. Moving dunes and shifting dust mean that over a few years, sand can creep toward landing pads, solar arrays, antennas, and buried cables. On Earth, sand can bury roads and buildings in deserts. On Mars, the same thing happens, just slower and under thinner air. So how extreme is the polar breathing from your point of view? Standing on the surface in a suit or inside a habitat? Mars's atmosphere is thin to begin with, around 6 to 7 millibars at the surface, compared with about 1,013 millibars at sea level on Earth. Over a Martian year, roughly 1/3 of that carbon dioxide freezes out onto the winter pole as dry ice, then comes back into the atmosphere when that pole tilts into sunlight again. The result is a global pressure swing on the order of 1/4 to 1/3 of the baseline. If your habitat is designed for a fixed external pressure, this cycle matters. Your airlocks, seals, and structural supports have to tolerate the constant loading and unloading. It's like living in a place where the sea level of the air itself rises and falls, not just the weather on top of it. If the atmosphere is thin and pulsing like that, why should you also care that it's escaping into space? Because it tells you Mars is mid-transition, not at a final stable state. Spacecraft like MAVEN have measured hydrogen and oxygen from water, and carbon from carbon dioxide, being stripped from the upper atmosphere by the solar wind at a rate of a few kilograms per second. In the short term, that doesn't change your day-to-day experience. In the long term, over hundreds of millions of years, it has already transformed Mars from a thicker, wetter world to the cold, dry surface we see now, if you're thinking about terraforming or even just about how the climate will drift over millions of years, you're not dealing with a closed box. You're trying to work with an atmosphere that has a built-in leak. So if you put all of this together, what's the correct way to think about Mars instead of dead red desert? A more accurate picture is Mars is a slow but active system, still cooling internally, still adjusting its crust, still moving ice, sand and gas around. It has marsquakes that show the interior is not fully frozen, young volcanic deposits that show it has erupted geologically recently, mobile dunes and dust that show the wind is strong enough to remodel a landscape, polar caps that drive big pressure cycles, and an atmosphere that is literally shrinking into space. None of those processes match Earth's intensity, but they are real. They are ongoing and they matter. And there's another consequence you shouldn't ignore. If the geology is still active, what does that say about the chances for some kind of biology, at least below the surface? Active geology means heat sources, fluid flow and chemical gradients. On Earth, those are exactly the conditions where microbes thrive, in deep rock fractures, hydrothermal systems, and under glaciers. On Mars, that could mean warm spots near old volcanic regions, salty liquid pockets near a buried ice, or slowly circulating brines at the base of debris-covered glaciers. No one has proved that life exists there today, but if you had to guess where to look, you'd look where the planet is still doing work. So the main point you should carry through this whole video is simple and sharp. Mars is not a static wasteland. It is a quiet but active world with multiple overlapping cycles, seismic, surface, ice and atmospheric, all running on slower timelines than you're used to on Earth, but all still running. Calling it dead is not just inaccurate, it makes you miss the real dangers and opportunities you'd face if you actually land there. And once you accept that the planet is still moving inside, one question becomes urgent. If the interior is active enough to shake the ground, what exactly are those marsquakes doing and how much trouble would they cause you on the surface? If Mars is supposed to be a dead planet, how do you explain the fact that the ground there has already shaken hundreds of times in just a few years of listening? You've got a lander called InSight sitting on the surface with a super sensitive seismometer, basically a machine that listens for vibrations in the ground. For nearly 4 Earth years, it just sat there and recorded. The result was more than 900 marsquakes. Some were tiny, just little pulses buried in the noise, but some were serious events, including one around magnitude 4.7 on the same scale used for earthquakes on Earth. That's not a city-destroying disaster, but it's strong enough that if you were nearby, you'd absolutely notice it. Your gear would rattle, loose rocks would shift, and you'd feel that deep, low-frequency motion that tells you the whole crust just moved as one piece. This is the key point. You don't get hundreds of quakes on a planet that's geologically dead. Quakes mean the crust is under stress right now. Something inside Mars is still cooling, shrinking, and trying to rearrange itself, and the outer shell is cracking and slipping to keep up. If Mars were just a frozen rock, a complete cinder, the seismometer would have heard almost nothing for years. So if Mars is shaking this much, where is most of that activity actually coming from, and why that place and not somewhere else? When scientists analysed the directions those quake signals came from, they kept pointing back to one region, Cerberus Fossae. It's a huge system of fractures, basically giant cracks in the crust, stretching for about 1,200 kilometres, roughly 750 miles. From orbit, you can see these long dark troughs slicing across older plains. That alone is a big clue. On a planet, younger features cut across older ones. So if these fractures slice through older lava flows, they must have formed later. There are not ancient scars from the early days of the planet, they're relatively recent tectonic structures. Now add the seismic data on top of that. The strongest marsquakes InSight detected trace back to this same region. That tells you Cerberus Fossae isn't just a set of old cracks that happen to be visible, it's an area where the crust is still being pulled, pushed, or bent today. The planet is literally trying to adjust its shape there. In simple terms, Mars hasn't finished settling down. and Cerberus Fossae is one of the places where that ongoing adjustment is loudest. You might hear magnitude 4 or 4.7 and think, that doesn't sound like much compared to the big earthquakes we talk about on Earth, so is this really a big deal? On Earth, you're used to a certain context. You have a thicker atmosphere, a lot of water in the crust, and a planet that's constantly resurfacing with plate tectonics and erosion. A magnitude 4 quake here is something you notice, but it doesn't usually make headlines. Mars is different. It's smaller, its crust is stiffer and more brittle, and the atmosphere is extremely thin. That changes how the shaking feels and how far it can travel. The rock on Mars transmits seismic waves efficiently because it's dry and cold, so a given amount of energy can be felt over a larger area. On top of that, there are observations of fresh boulder tracks around Cerberus Fossae. These are dark, narrow streaks where big rocks have recently rolled downhill, leaving a visible trail. They weren't there in older images, then they suddenly appear in newer ones. That's a strong sign that something shook those slopes hard enough to knock boulders loose. InSight Seismometer then comes in and confirms, yes, the ground out there is being hit with energy levels that match that kind of disturbance. So you've got a planet smaller than Earth, with a stiff crust and quakes large enough to trigger real rockfalls over and over again. It's not catastrophic on the scale of global extinction, but it's absolutely not background noise you can ignore if you're planning to put people and hardware on the surface. Alright, so the surface is clearly moving. What does that actually tell you about what's going on deeper inside Mars? Seismology is basically remote sensing for the inside of a planet. You don't need to drill 1,000 kilometers down, you send waves through the interior and see how fast they travel, how they bend and how they reflect. Different layers, crust, mantle, core, have different densities and different physical states, solid or liquid. From marsquakes, scientists have been able to estimate that Mars has a crust around 24 to 72 kilometers thick, roughly 15 to 45 miles. Under that, there's a mantle that's still warm enough to slowly flow over very long timescales, a process called convection. And deeper still, the core is not solid throughout. The data are consistent with a core that's at least partly liquid. If the core were completely solid and the mantle fully frozen, the planet would be almost silent seismically. Instead, the interior is still losing heat, material is still moving slowly, and that motion is putting stress on the crust. The absence of a strong global magnetic field tells you the core isn't convecting in the right way to power a full dynamo anymore. But the presence of marsquakes and a warm mantle tells you the system isn't finished. Mars is in a middle state, not fully active like Earth, not fully shut down like a small asteroid. It's still cooling, still rearranging its insides, and you can literally hear that through the quakes. So let's bring this back to you. If you were actually standing there, would you feel these marsquakes? And how much risk are we really talking about for a human base? If you built a base in or near an active zone like Cerberus Fossae, you wouldn't treat the ground as perfectly still bedrock. A magnitude 4 to 4.7 event close by is enough to shake equipment, jostle regolith shielding, and trigger small collapses in any loose material nearby. Even smaller, more frequent quakes could slowly weaken slopes and structures over time. You wouldn't want your main habitat right under a steep cliff face or next to a tall, unsupported regolith berm. The right approach would look a lot more like how engineers design buildings in seismically active areas on Earth, like coastal California, than how you'd build in the middle of some supposedly rock-solid desert. You'd use flexible joints, structures that can sway a bit instead of cracking, wide bases with a low centre of gravity, and careful anchoring into the ground. Heavy items like water tanks or regolith blocks for radiation shielding need to be secured so they don't shift or topple when the ground moves. On top of that, you'd treat seismic monitoring as part of normal operations. You would have your own seismometers running all the time, and you'd keep an eye on patterns, locations, and frequencies of quakes. If a particular region started to light up more often, or if you saw a cluster getting closer to where you are, you might change how you use certain areas, or even decide to move some critical hardware. So Mars is not giving you city-flattening megaquakes every week, but it is absolutely not a silent rock. The shaking is strong enough and frequent enough that future bases will have to respect it, and if you ignore that, you're basically designing for a planet that doesn't exist. Now here's the next problem this raises. If Mars is shaking and the crust is under stress, what's actually feeding that from below? And how recent is the last time that deep interior heat broke through to the surface as real volcanism? How do you know Mars hasn't switched its volcanic engine off for good? You look where the evidence is most uncomfortable, Elysium Planitia, the region that basically refuses to die. This area sits close to Cerberus Fossae, the same noisy fracture zone you just heard about with all the marsquakes. From orbit, high-resolution cameras see something that should not exist on a dead planet. Dark, sharp-edged deposits lying on top of older, smoother lava plains. The older plains are classic basaltic lava, wide, flat flows that have been beaten up by the impacts and dust for a long time. The newer stuff is different. It's darker, less cratered, with crisp boundaries. When scientists counted impact craters on these dark surfaces, which is the standard way to estimate ages on airless or thin-air worlds, the numbers came back shocking. Some of these deposits are in the range of about 53,000 to 210,000 years old. Not hundreds of millions, tens of thousands. On a 4.5 billion-year-old planet, that is ultra-recent. So what does 53,000 years actually mean when you stop thinking like a human and start thinking like a geologist? On Earth, 53,000 years ago, there were already humans leaving art on cave walls. That's younger than a lot of our own culture. For Mars, 53,000 years ago is basically now. When planetary scientists say a feature is tens of thousands of years old, they don't say extinct, they say potentially active. If a volcanic system produced ash in that time window, it is not honest to treat it as a fossil. You have to treat it as a system that could, under the right conditions, erupt again. Maybe not next year, maybe not in your lifetime, but on Mars's internal clock, it hasn't finished its run. So the natural question is, what could keep a patch of Mars this hot, this late in the game? The surface is cold, the air is thin, the core has lost its global magnetic field. Where does the energy for recent volcanism actually come from? The leading idea is a mantle plume under Elysium Planitia. A mantle plume is basically a broad column of hotter than average rock rising very slowly from deep inside the planet toward the underside of the crust. It's still solid overall, but it's soft enough to flow on million-year timescales. On Earth, plumes feed volcanic hotspots like Hawaii and Iceland, areas of focused volcanism away from plate boundaries. On Mars, which doesn't have Earth-style plate tectonics, plumes are even more important because they can sit in one place for a long time, delivering heat to the same region again and again. In Elysium Planitia, a plume would neatly explain two things at once: the relatively young lava and ash deposits on the surface, and the cluster of marsquakes recorded by InSight not too far away. Rising hot rock pushes up the crust slightly, stretches it, and can open fractures like Cerberus Fossae. At the same time, it can melt portions of the mantle and generate magma that rises and erupts. The quakes are the crust adjusting to that stress. The dark young deposits are the frozen record of magma that actually reached the surface in the geologically recent past. So how big are these eruptions when they happen? Are we talking about minor burps or full-scale floods of lava? The numbers point to serious volumes. Flood lavas in this wider region are estimated to have reached thousands of cubic kilometers. To make that intuitive, one study gives a figure around 5,000 cubic kilometers for certain earlier outbursts. That's 5,000 billion cubic meters of rock. If you spread that out over an area the size of the US state of Massachusetts, you could bury it under about 300 meters of lava, roughly 1,000 feet. That's higher than most skyscrapers. In metric terms, that is a layer as tall as a 100-story building, made entirely of solidified basalt. Even if individual more recent eruptions are smaller, you're still dealing with flows and ash fields that can cover tens to hundreds of square kilometers, tens to hundreds of square miles, in layers tens of meters thick, tens of yards to a few hundred feet. This is not some tiny vent quietly dripping a bit of lava. This is large-scale resurfacing. So what does that actually mean for the environment around those eruptions beyond just, wow, that's a lot of melted rock? Fresh volcanism changes chemistry and habitability at the same time. When magma rises and erupts, it doesn't just deliver lava, it also releases gases. Common gases include water vapour, carbon dioxide, sulfur dioxide, and other sulfur compounds. Even on Mars, where the atmosphere is thin, a local eruption can temporarily thicken the air above it, inject heat, and change the local climate on short timescales. More importantly, that heat can melt buried ice. If you have a layer of frozen water a few meters or tens of meters below the surface, and a hot dike of magma cuts through it, you can briefly create pockets of liquid water or very salty liquid called brine. Combine that with volcanic gases and fresh mineral surfaces, and you get exactly the kind of chemically rich environment that microbes on Earth love. Think about deep-sea hydrothermal vents, volcanic caves, and hot springs in our own crust. Life there doesn't need sunlight. It runs off chemical gradients, reacting things like hydrogen and sulfur with other compounds. On Mars, a plume-fed volcanic system in Elysium Planitia could have created, and maybe still creates occasionally, small subsurface zones that look like that, pockets of warm, wet, reactive rock. For humans, those same processes cut both ways. On the positive side, heat sources in the crust, and the leftover structures from past eruptions might be places where you can tap geothermal gradients or find concentrated deposits of useful minerals. On the negative side, you're dealing with ground that has a history of being reshaped by lava, broken by faults and shaken by quakes. You'd be very careful about putting a long-term base right on top of the youngest deposits there. You'd probably want to operate like we do around active volcanic fields on Earth, keep a healthy distance, monitor the ground constantly, and treat the region as both a science goldmine and a long-term hazard. So now the picture is getting sharper. Mars isn't just a planet that quakes a bit, it's a planet that, in at least one region, has produced actual volcanic ash and lava in what, geologically, counts as the present. That means internal heat is still concentrated enough in places to melt rock, crack the crust, release gas, and maybe even create short-lived habitats for microbes in the subsurface. If Mars can still melt and move rock from the inside like this, the next question is obvious. What is its thin, cold atmosphere doing to the surface from the outside over years and decades, especially to all that loose sand and dust? If Mars is supposed to be frozen and quiet, why are hills of sand up to 60 meters high, about 200 feet, actually sliding across its surface right now? For a long time, most scientists thought the big sand dunes on Mars were fossils, relics from an era when the air was thicker and winds were stronger. The idea was, the climate changed, the winds weakened, and the dunes just stayed where they were, like a snapshot from the past. Then we got real before and after pictures. Orbiters with high-resolution cameras took images of the same dune fields years apart, and when people overlaid them, the outlines didn't match. Whole dunes had shifted. Some had moved by about 1 meter per Martian year, roughly every 1.9 Earth years. These aren't little ripples. These are dunes up to around 60 meters tall, 200 feet, drifting over the ground a meter at a time. On a human timeline that feels slow, on a planetary surface that's very fast. So here's the question that should bother you. How do you move that much sand in air that thin? Mars' atmosphere at the surface is only about 6 to 7 millibars, less than 1% of Earth's sea level pressure, which is around 1013 millibars. At that pressure, your blood literally boils without a suit, so this is not some thick, stormy sky. To move sand grains, the wind has to hit a certain threshold speed right at the surface. In such thin air, that threshold is high, you need strong gusts. But once grains start to move, Mars cheats in a different way. Gravity is only about 38% of Earth's. That lower gravity makes it easier to lift grains off the ground and keep them bouncing in short hops. Each grain that hops can hit others, knock them loose, and start a chain reaction. You end up with something called saltation. Sand grains jumping along the ground, hitting, bouncing, and pushing others. Each individual hop might only be tens of centimeters, inches to a few feet, but over millions and billions of hops, and over years and decades, dunes migrate. You don't need constant hurricane-force winds. You just need enough strong gusts, often enough, combined with low gravity, to keep the transport going. That's exactly what the images show, dunes creeping forward year after year. If individual dunes can move like that, what happens when you zoom out and look at an entire region instead of a single hill? In the north of Mars, around the edge of the polar cap, there's a wide belt of dune fields. The total area is on the order of a large US state roughly comparable to Texas. So we're talking hundreds of thousands of square kilometers, hundreds of thousands of square miles. These aren't smooth, dead plains. They're packed with dark dunes and ripples that stand out sharply against lighter underlying material. When orbiters take repeated images over several Martian years, the changes are obvious. Small ripples migrate across the surfaces of bigger dunes. Steep slip faces, the downwind sides of dunes where sand avalanches collapse in new places. Dark sand spills over bright dust-covered ground, leaving new streaks and patches. None of that happens if the wind is too weak to move grains. These patterns are the fingerprints of active transport. Sand being picked up, carried and dropped over and over again across entire regions. So if you were actually there next to one of these dunes, not just looking from orbit, what would you see on a human timescale? If you camped near a dune for a full Martian year, almost 2 Earth years, you'd probably notice small but real changes. The fine ripples on the surface of the dune might shift by tens of centimeters, on the order of a foot or so. The crest of the dune could creep forward by fractions of a meter, maybe a few tens of centimeters, depending on local wind conditions. You might see small avalanches where sand builds up to a critical angle and then suddenly slides down the slip face, especially after a series of gusts or when nighttime frost forms and then sublimates at sunrise. These are not dramatic instant collapses like in a disaster movie, they're fast microgeology. But over a decade, which is a realistic time span for a human outpost, that microgeology adds up. A dune front moving a meter every Martian year can close a 10-meter gap, about 33 feet in around 10 Martian years. That's directly relevant if you have a landing pad, a road, a field of solar panels or buried cables nearby. What looks like plenty of clearance at the start of a mission can turn into, we need to dig this out if you don't plan for it. So why is this moving sand such a big deal for the idea of a living Mars instead of just an engineering headache? Because dunes that move mean the atmosphere is doing real mechanical work on the surface right now. To push hundreds of billions of grains of sand across an area the size of a continent-scale region, you need sustained wind patterns, not just one random gust. Those wind patterns are driven by temperature differences, pressure differences, and seasonal cycles. On Mars, one of the biggest drivers is the CO2 cycle at the poles, where a large fraction of the atmosphere freezes out in winter and returns in spring, changing global pressure by about 25 to 30%. That breathing cycle feeds into wind speeds and directions. Put it all together. And mobile dunes are not just a curiosity. They're evidence that the climate system is active, that pressure is swinging, that winds are strong enough often enough to rearrange the ground on kilometre scales, miles across, over just a few years to decades. A truly dead, static world doesn't keep reshaping its deserts like this. It might have dunes, but they'd be locked in place for millions of years. Mars is not doing that. Mars is currently reshaping its sand seas. For you, as a future visitor, this matters on 2 levels at once. On the practical side, moving sand is a hazard. It can bury hardware, erode surfaces, and change local terrain in ways that affect landing and driving. On the scientific side, it's a clear, ongoing heartbeat of the atmosphere, telling you that this planet's surface is still responding to changes in ice, sunlight, and pressure every single year. And that leads straight to the next, more disturbing question. If the wind can move dunes like this under normal conditions, what happens to the atmosphere and to the entire surface when up to a third of that already thin air freezes solid at the poles and then comes back every year? How do you call a planet dead when it literally freezes and unfreezes part of its own atmosphere every single year? On Mars, up to about 1/3 of the entire carbon dioxide atmosphere doesn't just cool down a bit in winter, it actually turns solid at the winter pole. The CO2 gas in the air hits those polar night temperatures, drops below its freezing point, and forms a seasonal cap of dry ice on the surface. Then when spring sunlight returns, that dry ice doesn't melt into liquid, it goes straight back to gas. So across a Martian year, you have a chunk of the atmosphere physically moving from gas to ice and back. On Earth, that would be like Antarctica grabbing around 30% of our air, locking it up as dry ice for a few months, then dumping it back into the sky. That's not normal weather. That's the whole planet running a huge regular mass transfer cycle. So does this just show up in graphs and models? Or would you actually notice it if you were standing there in a suit? You would absolutely notice it. As that CO2 freezes out at one pole and then resublimates and flows toward the other, the total amount of gas in the atmosphere changes. Surface air pressure across the whole planet swings by roughly 25 to 30% over a Martian year. Remember, Mars already sits at only about 6 to 7 millibars at the surface under 1% of Earth's sea level pressure of about 1013 millibars. So a 30% change on Mars is not huge in absolute terms, but it's big compared to the tiny baseline. If your suit has a sensor showing ambient external pressure, that readout would slowly drift up and down as the year goes on. Same for a habitat. The structure is pressurized from the inside to something human-friendly, but the outside push from the air is not constant. Every lander, every base, every airlock has to be designed for that breathing baseline, not just a single number. Seals, hulls and pressure vessels will see a repeating cycle of load and unload as the poles inhale and exhale CO2. Over years, that cycle affects fatigue, just like repeated small flexing eventually weakens metal if you don't account for it. So the air is moving on a planetary scale. What about the ice itself? Is it just a static cap under all this? Or is it reshaping the surface too? The polar caps are not just big quiet ice sheets. They grow and retreat with the seasons and over longer climate cycles. They're built up of layered deposits, alternating bands of ice and dust that record those swings. In winter, seasonal frost spreads beyond the permanent cap, coating dunes and slopes. In spring, that thin frost layer doesn't just gently fade away. In many places, it breaks, slides, and sublimates in active ways. Here's what that means in practice. You can get thin slabs of CO2 frost that slide downslope like a slow, dry avalanche. Gas building up underneath the ice as it warms can jet out and blast loose material. When the frost disappears, it leaves behind new streaks, small gullies, and disturbed patches. On steep crater walls and cliffs, the repeated cycle of frost deposition and loss can destabilize the surface, helping trigger small avalanches of soil and rock. That's active geomorphology, ice and frost doing mechanical work on rock right now, not just sitting there as a relic. So it's not just that the air and the ice are moving. We can actually measure the planet's response in a way that sounds almost ridiculous. How do we know how much mass is shifting beyond just images? Orbiters can sense tiny changes in Mars's gravity field as the CO2 moves between atmosphere and polar caps. Gravity depends on how mass is distributed inside and on a planet. When you pile a huge amount of frozen CO2 onto one pole, you slightly increase the gravitational pull in that region. When that CO2 goes back into the atmosphere and spreads around, you change the distribution again. These changes are small, but modern instruments can detect them by tracking slight accelerations of the spacecraft. So we're not guessing here. We can see the caps grow and shrink, we can measure the pressure swings at the surface, and we can even pick up the gravity signal from the mass transfer. When a planet is shifting enough material around each year to tweak its own gravity field in a measurable way, you are not dealing with a frozen, unchanging world. You're watching a system with a real, ongoing heartbeat. Now, why does this matter for the rest of the climate and for you, beyond being a cool fact about ice? Because those pressure swings are not just numbers on a plot, they drive winds and dust activity. When CO2 sublimates at the warming pole, the newly released gas expands and flows toward colder regions and lower altitudes. That movement of gas is wind. On Mars, wind is the main driver of most near-surface change. It picks up dust, carries it, and drops it somewhere else. It sculpts dunes, erodes rock faces, and sandblasts hardware. Think of the polar caps as pistons in a huge atmospheric engine. Each Martian year, they pump CO2 into and out of the air, modulating pressure and pushing air masses around the globe. That pumping feeds into jet streams, regional winds, and local gusts. When those winds interact with loose dust and sand, you get everything from small dust devils a few meters across, a few yards wide, to storms that can wrap the entire planet. For you as a future explorer, that means the poles are not just pretty features far away at high latitudes. Their behaviour sets the baseline your mission sits on. They help decide how strong typical winds are, how often sand is mobilised, how likely dust is to build up on your solar panels, and how the atmosphere responds to sunlight over the year. They are part of the control system for dust and storms that can change your available power and visibility for weeks or months. So here's the uncomfortable next step if the poles are driving this massive breathing cycle, and if that cycle feeds directly into the winds and dust. What happens when conditions line up just wrong and the entire atmosphere flips into a full planet-encircling dust storm that can shut down solar power and bury a rover for good? How dead can a planet be if one storm can turn the whole sky dark and quietly kill a working robot? In 2018, a local dust storm on Mars ramped up, linked with other systems, and within a few weeks had grown into what scientists call a planet-encircling event. Not a regional haze, not a bad weather patch, but dust wrapped around almost the entire globe. The air was already thin to begin with, but now it was packed with fine particles. Daytime skies turned from clear butterscotch to a solid, dirty orange. Sunlight at the surface dropped so much that solar panels stopped producing useful power. The Opportunity rover, which had been operating for nearly 15 Earth years, went to sleep to conserve energy and never came back. Its batteries got too cold, too depleted, and that was it. One storm, one feedback loop, and a working robot turned into a permanent monument. So how does something this extreme happen in air that's less than 1% of Earth's pressure? Mars's atmosphere is thin, but the dust grains are tiny and light, measured in micrometers. Once you kick them up, they don't fall out quickly. Winds lift dust from the surface in local storms and dust devils. Those grains absorb sunlight high in the atmosphere, heating the upper layers. At the same time, the dust blocks some sunlight from reaching the ground, so the surface cools relative to the air above. Now you've set up a strong temperature difference with warm air over cooler ground. That temperature contrast changes how air flows. Winds shift, strengthen in certain layers, and start lifting even more dust from more places. You get a feedback loop. More dust in the air means more heating aloft and more shading below, which means stronger circulation patterns, which pick up more dust. The atmosphere might be thin, but vertically it becomes a powerful system with energy being pumped into it from sunlight hitting all those dust grains. Once the loop crosses a certain threshold, the storm stops being a local problem and starts spreading across half the planet, then more. So is this just a one-off freak event, or did we actually watch the whole process with multiple sets of eyes? During that 2018 storm, Mars was not being watched by just one spacecraft. There were 6 orbiters from different space agencies and 2 rovers on the ground feeding data back. They were recording temperature profiles at different heights, measuring how opaque the air was to sunlight, tracking how the storm front moved and estimating wind speeds. As the storm grew, instruments saw the upper atmosphere heat up while the surface cooled, exactly what you'd expect from dust-absorbing sunlight high up. The rovers saw their power drop as sunlight at the surface faded. Orbital images showed features on the ground becoming harder and harder to see as the haze thickened. Then months later, as the storm decayed, all those measurements slowly shifted back toward pre-storm values. That behaviour is not what you see from a dead, barely reacting shell of gas. It's what you see from a dynamic atmosphere that can be pushed into a different state and then relax back, like a system with real levers and real thresholds. So how often does Mars pull this kind of move? Is this a constant nightmare or an occasional punch? Global planet-encircling dust storms don't happen every Martian year. If they did, Opportunity would never have lasted as long as it did. Based on decades of observations, they show up every few Martian years on average. Sometimes they're stronger, sometimes weaker, and there's no perfect schedule you can set your watch to. That irregularity is important. If they were locked to a simple pattern, the climate would be more predictable. Instead, small differences in starting conditions, local storms, and seasonal timing can decide whether a given year gets a normal dust season, a big regional storm, or a truly global event. For you planning to live there, that's a serious design constraint. You're not facing the sudden, sharp impact of a hurricane like on Earth, with winds at many tens of meters per second and destructive rain. You're facing weeks to months of reduced sunlight, abrasive dust in the air, and a slow grind of erosion. Think of it as a long, drawn-out storm season made of dust, not water, that can drop your solar power output to a fraction of normal and keep it there long enough to drain batteries and stress systems. Nuclear power helps, but not every mission will have that luxury. So what are these storms doing to the surface while all this is going on, beyond choking off sunlight and killing solar rovers? Every dust storm, regional or global, is a sandblasting event. Fine grains hit exposed surfaces at speed and chip away at them. Over one storm, you might only remove a thin layer of material from rocks and hardware, but repeat that over thousands of storms, and you can round sharp edges, polish rock faces, and erase small impact craters. Dust is also constantly being moved from one place and dropped in another. Depressions can fill, subtle features can be buried, and thin dust layers can be stripped away to reveal fresh rock or ice. On long time scales, thousands to millions of years, these repeated storms help remodel Mars deserts. They smooth some areas and roughen others. They cover some patches of subsurface ice and uncover others, changing where future explorers might find easily accessible water. The desert you would land in today is not exactly the same desert that was there a few million years ago, and it won't be the same a few million years from now. For you standing on the surface with a habitat and a fleet of vehicles, all of this turns into very practical problems. Dust infiltrates seals, joints, and moving parts. It settles on radiators and solar panels, cutting performance. It can reduce visibility for cameras and human eyes. A global storm means you need energy reserves that can last for months, life support systems that can cope with lower input power, and hardware that can survive extended exposure to abrasive particles under low-pressure, cold conditions. It's not a single high-G impact, it's a long, grinding test. Taken together with the breathing poles and the walking dunes, these planet-scale dust events tell you something blunt. Mars has an active climate system, even if it's thin and cold by Earth standards. It can switch state, amplify small disturbances, and reshuffle the surface again and again. That is not what a dead world looks like. So once you accept that the air can flip from clear to choked and back, the next question is, what's hiding under that shifting cover of dust and ice, and how stable is the ground itself when you look at glaciers that are not gone, just buried? How sure are you that the rock you'd be standing on in Mars's mid-latitude is actually rock, and not ice hiding under a thin skin of rubble? When you look at certain regions between the poles and the equator, you see strange, lumpy flows running out from the bases of mesas and along valley floors. They look like tongues of broken rock frozen in motion. These are what scientists call lobate debris aprons and lineated valley fill. For a long time, people argued about what they were made of. Then radar instruments on orbiters started probing the subsurface. The radar signals bounce back in a way that only makes sense if the bulk of that material is low-density solid ice, not solid rock, with just a thin layer of rocks and dust on top. We're talking about structures hundreds of meters thick, in some cases approaching a kilometer, so hundreds to more than 1,000 feet of mostly water ice armoured by debris. In plain language, those rock flows are glaciers, just buried and disguised. If they're glaciers, the next obvious question is, did they actually move like glaciers, or are they just static blocks that happen to form that way and then froze in place? Their surfaces answer that for you. High-resolution images show ridges and folds running across them, and patterns people call brain terrain, because they're made of tight, curved grooves that interlock. Those shapes are not random. On Earth, you see the same kinds of features in glaciers and ice streams where ice has deformed and flowed over obstacles and down valleys. The lineated texture in valley fill points in the direction of past movement, like flow lines painted into the surface. When you model how a thick, cold, debris-covered ice body would behave under Martian gravity and temperature, you get exactly these kinds of features if it has flowed like a very slow, very thick fluid. The ages we get from crater counts tell you when that movement was most active, somewhere in the last 100 million to 1 billion years. On a 4.5 billion-year-old planet, that's a recent episode. Those glacial periods would have reshaped whole regions, dumping ice into mid-latitudes under conditions where the climate allowed it to survive. So you're not looking at ice that's been sitting there since the dawn of Mars. You're looking at the leftovers from relatively recent climate swings. So if they once flowed, are they still moving today at all, or are they finally locked up for good? Right now, the flow is probably extremely slow. Models suggest rates on the order of centimetres per year or less, so under an inch per year. That sounds like nothing, but it's still motion. Over a human lifetime, that can add up to meters of shift in the ice mass beneath the debris cover. Over a century, it's even more. If you build something heavy directly on top of one of these buried glaciers, you're building on a very slow conveyor belt, not on stable bedrock. Structures could tilt slightly, foundations could creep, and anything relying on precise alignment could drift out of spec. At the same time, the fact that this ice is still there, and still mostly intact, tells you something important about today's environment. The subsurface is cold and dry enough, and the debris cover is thick enough to protect the ice from simply sublimating away into the thin atmosphere. If the climate had been totally stable for billions of years, you wouldn't get big ice bodies dumped into mid-latitudes like this in the first place. The fact that the ice has clearly flowed in the past and is now preserved tells you Mars' climate has changed and is still in a state where these glaciers can survive for a very long time. So why should you care about this ice beyond the engineering headache of slow ground movement? Because these buried glaciers are massive ready-made water supplies. A single glacier can hold billions of cubic meters of ice. At about 1,000 kilograms per cubic meter, that's billions of tons of water. For future explorers, that is a resource you can turn into drinking water, breathable oxygen, and hydrogen for rocket fuel. You don't have to haul that mass out of Earth's gravity well, you just have to dig, drill, or melt. And because these glaciers sit in mid-latitudes, they're much easier to reach than the permanent caps at the poles. Temperatures are less extreme than at the poles, and sunlight is more favourable for solar power. The debris cover on the top also helps you. It shields the ice from direct sunlight, making it more stable over long periods, so you're not racing against rapid loss into the atmosphere. You can think in terms of mining a buried reservoir the size of a small city, not scraping frost off rocks. But they're not just water tanks, they're data logs of Mars's climate. So what are they telling us about how wild that climate has been? Layered structures inside these glaciers, and the way radar waves bounce off different depths, carry information about how conditions have changed over time. On Earth, we use ice cores and internal layers to track past temperatures, snowfall, and even atmospheric composition. On Mars, we can't yet drill deep cores out of these mid-latitude glaciers, but radar already shows internal layering and changes in density that line up with cycles we expect from how Mars' axis tilts over time. Mars doesn't have a big moon like Earth to stabilise its tilt. Its obliquity, the angle between its spin axis and its orbit, can swing dramatically over millions of years. When the tilt is higher, mid-latitudes get more sunlight, poles can lose ice, and ice can migrate toward lower latitudes, feeding exactly the kind of glaciers we see as lobate debris aprons and lineated valley fill. When the tilt is lower, conditions change again and the ice flow slows or stops. The patterns inside these glaciers, and their distribution across the planet, are one of the reasons we say Mars' climate history is chaotic, with big swings, not a flat, unchanging line. For you, that matters in two ways. First, those layers are how we reconstruct what Mars has been doing for the last few 100 million years, which feeds into models of how it will behave in the future. Second, the fact that so much ice moved into these regions in relatively recent times and is still there tells you the planet is partway through a long-term redistribution of water, not at a final endpoint. So now you've got dunes that walk, poles that breathe, storms that wrap the globe, and glaciers that slowly creep under a fake rocky surface. If even the ground that looks solid can move, what do you think is happening on the steep slopes and crater walls, where gravity has a much easier time tearing material loose? How stable do you really think a Martian cliff is when the surface is covered in fresh scars that weren't there the last time we checked? High-resolution images from orbit show small branching channels, these gullies, cut into crater walls and steep hillsides all over Mars. They don't look worn down and ancient. They have sharp edges, bright streaks, and very few impact craters on top of them. That alone already tells you they're young, but there's harder evidence. When you compare images of the same slopes taken years apart, you find new flows, fresh deposits that weren't there before. A patch that looks smooth in one picture suddenly has a fan of bright material in the next. That means these gullies are not just relics from some distant past climate, they're being modified in the current one. Materials coming loose, sliding down slope, and settling in new shapes while we're watching. So what's actually making that material move now, in the thin, cold atmosphere? There's an active argument about that. One camp points to seasonal carbon dioxide frost. In winter, CO2 from the atmosphere freezes out on the shady slopes as a thin layer of dry ice. When spring sunlight hits, that dry ice doesn't melt into liquid, it goes straight back into gas. If gas builds up underneath or within the frost layer, it can vent suddenly, pushing loose soil and rock downhill in what is basically a dry avalanche driven by gas pressure, not liquid water. Another camp says you can't rule out occasional salty water, brines, especially in certain temperature and pressure windows. Salts like perchlorates can pull water out of the atmosphere and lower its freezing point, letting thin films or trickles form briefly before they evaporate or freeze again. The key thing for you is that the details of the mix don't change the main conclusion. Whether it's mostly CO2 frost, mostly brines, or both, the slopes are not stable. Materials moving downslope in today's climate. The surface is responding to present-day conditions, not just to ancient floods or glaciers. When you see a new gully deposit appear between orbital passes, that's Mars telling you directly, I am still reshaping myself right now. If small slopes are this active in the current climate, what about the really big failures? Are those all ancient, or are some of them geologically recent too? When you zoom out from small gullies to giant landslides in places like Valle Marineris and other deep canyons, you see massive chunks of rock that have broken off cliffs and collapsed. We're talking structures tens of kilometers long, many kilometers wide, and hundreds of meters thick, so miles across and hundreds to thousands of feet deep. Crater counting and morphology studies put the ages of some of these big landslides under about 20 million years. On a human timeline, that's unimaginably old. On a 4.5 billion year planet, that's very recent. The landslide deposits look sharp with blocky textures and clear boundaries. They're not softened and erased by billions of years of impacts and dust. That tells you gravity and internal stresses have been actively cutting down cliffs and canyon walls in the geologically recent past. And in many cases, there are smaller, fresher flows and streaks sitting on top of those big deposits, showing that the story didn't stop when the main collapse happened. The surface is being refreshed by more than just occasional impact craters and a slow drizzle of dust. Big chunks have fallen and smaller material keeps following. So what actually pushes those cliffs over the edge? Is it just gravity waiting long enough, or is something else giving them a nudge? This is where the marsquakes you heard about earlier come back in. Take a steep slope, add layers of loose material from dust, frost and old deposits, and then shake the ground. You don't need a magnitude 8 monster for that to matter. On Mars, even a magnitude 4 event, especially near an active fault zone, can jolt unstable material loose. Add in the stress of daily and seasonal temperature changes, and the expansion and contraction from frost cycles, and you have a system that's constantly being loaded just a little more. Some of the narrow slope streaks you see in images, and some of the fresh deposits at the base of cliffs, might literally be the result of individual quakes, marsquake fingerprints. A crustal adjustment deep below sends waves through the rock. The waves reach a slope that's close to failure, and a patch of regolith finally lets go and slides. You don't see the quake from orbit, but you see the aftermath as a new streak or fan. Over time, that repeated process eats away at cliffs and walls, even without liquid water doing the erosion. So what does all of this mean if you're not just visiting in a simulation, but actually trying to build a base and stay alive there for years? On Earth, you don't put your main buildings right under an active rock face in a seismically active area. The same logic applies on Mars, but with extra factors stacked against you. The lower gravity means material can pile up into steeper slopes before failing, so when failures happen, they can be larger relative to the height. The dry, brittle regolith doesn't have cohesive plant roots or moisture binding it together the way some soils do on Earth. CO2 frost cycles can weaken surfaces in ways you're not used to. And marsquakes, even if modest in size, give you periodic kicks, so you treat slopes with suspicion. Before you pick a landing site or a base site, you map nearby cliffs, crater rims, and hillsides in detail. You look for active gullies and streaks. You compare old and new images to see if anything has changed recently, and you set wide safety zones around any slope that shows signs of motion. You design your hardware and surface routes with the assumption that small collapses will happen over a mission lifetime. You keep sensors watching key slopes, so you can spot new streaks or bulges early, instead of finding out about them when part of your access road disappears. This is not a static rock face you can ignore once and forget. It's a slowly crumbling, constantly adjusted surface that will keep shifting on timescales that overlap with human missions. Treat it like dead terrain, and you'll eventually lose something important in a slide. And here's the next question that raises the tension even more. If the obvious cliffs and gullies are this active, what about the subtle dark streaks that appear, grow, and fade on warm slopes, some of which come back year after year? Are those just dust? Or are they telling you something deeper about liquid, chemistry, and a surface that keeps flickering between states? How do you explain a planet that keeps drawing dark lines down its own slopes, then erasing them, then drawing them again? On Mars, you see these features called recurring slope lineae, or RSL. In plain terms, they're narrow dark streaks that show up on warm slopes, grow downhill over the course of a season, then fade when it gets colder. Next warm season, they come back, often in almost the same places. They tend to start near rocky outcrops or boulder clusters and can stretch for hundreds of meters, so hundreds of yards down crater walls and hills. From orbit, they look like thin, finger-like smudges running downhill. The key thing is the timing. They track temperature, not random impacts. That alone tells you something in the environment is switching on and off on timescales you can follow with a calendar, not just with a geology textbook. When scientists first saw RSL and then detected hydrated salts at some of those sites, the obvious exciting idea was salty liquid water. Salts like perch laurets can pull water out of the air and drop the freezing point far below 0 degrees Celsius, below 32 degrees Fahrenheit. So even in Mars' cold, thin atmosphere, you could, in theory, get very salty brines forming briefly when it's warmest. Thin films of liquid could trickle through the top layer of soil, darkening it and making streaks as they go. Then, as temperatures drop and the air dries, the water evaporates or refreezes, and the streaks fade. If that were the full story, it would be huge. Liquid water, even very salty, is one of the strict requirements for life as we know it. It doesn't guarantee microbes, but it opens a real door. But as more data came in, the picture got more complicated. Larger surveys, including machine learning studies that combed through hundreds of thousands of slope features, started to show patterns that were less friendly to the "it's all brine" idea. Many dark streaks showed up in places that didn't match where liquid should be easiest to form based on temperature and humidity. Instead, they lined up better with dust patterns, impact sites, and slopes that are especially prone to dry avalanches. Some RSL-like features seem to be triggered by events like small impacts or wind gusts, where dust is disturbed and darker material underneath is exposed. That led to a different explanation for at least a large fraction of these streaks, dry processes. In that view, you don't need flowing water at all. A small disturbance, maybe from a rockfall, a tiny quake or frost forming and vanishing, can destabilize the top dust layer. It slides down slope, revealing darker material beneath. The streak looks dark at first, then slowly brightens again as fresh dust settles back onto it over months or years. The process can repeat when conditions line up again. For many sites, the statistics and the physics fit this dry scenario very well. So where does that leave you? It leaves you with a planet that still refuses to sit still, no matter which mechanism dominates at a given site. Whether a particular streak is caused mainly by brine, by dust avalanches, or by a mix, the important point is the time scale. These things appear, grow, fade, and then reappear over months to a few years. You can see changes between one Mars year and the next. They are not fossils from some ancient wet era that just happen to be preserved. They are ongoing surface processes in the current climate, processes you could track during a single human mission with nothing more complicated than a decent camera and a good archive. For you as a future explorer, these spots are double-edged. On one side, they're hazard flags. A slope that regularly produces RSL or other active streaks is telling you it is close to failure, that material there is marginally stable and can move under small triggers. You don't put your base, your fuel tanks, or your main vehicle depot at the base of a slope that keeps shedding material. Landing directly on or above such features would be asking for trouble, because the ground is quite literally known to change under current conditions. On the other side, these sites are extremely valuable scientifically. They mark places where the subsurface, the atmosphere, and gravity are interacting right now. If brines are involved, even rarely, these are direct clues about how and where liquid can exist on modern Mars, and for how long. If the processes are mainly dry, they still tell you about how dust moves, how slopes fail, and how surface materials respond to tiny changes in temperature and pressure. For life detection missions, RSL-type sites are exactly the kind of boundary zones you want to understand, even if strict planetary protection rules might keep you from driving a rover right into them at first. The bottom line is, Mars's surface is flickering. It's not one static pattern of dust and rock frozen for 1 billion years. It's a set of features that come and go, some of them repeating with the seasons, some triggered by random events but still happening in the present. You could send a rover, park it with a good view of an active slope, and watch new lines and fans appear over the course of a few Martian years. That is a living, changing surface by any reasonable definition. And that brings up a bigger, more uncomfortable question. If the slopes, dunes, and dust patterns are this restless, what about the air itself? Is the atmosphere at least stable, or is Mars also quietly losing that to space, kilogram by kilogram, while all of this is happening on the ground? If Mars is supposed to be a finished world, why is the planet still losing parts of its air into space right now, second by second? The thin gas above your head on Mars is not submersible. Spacecraft like MAVEN have measured hydrogen and oxygen mainly coming from broken up water molecules, drifting away from the top of the atmosphere and getting stripped by the solar wind. Add it up and the loss rate is roughly 2 to 3 kilograms every second. That's a couple of kilograms of gas, leaving the planet all the time with no pause button. It's not a theoretical once long ago thing, it's a number you can write down today. You might hear 2 to 3 kilograms per second, and shrug because that sounds small, so does this actually matter over the lifetime of a planet? On human timescales it's nothing. On geological timescales it's huge. 2 kilograms per second is about the mass of a brick every second. Multiply that by a year, you're in the tens of millions of kilograms. Multiply that by 1 million years, now you're in the 10 to the power of 13 kilogram range. Keep going into hundreds of millions of years, and the total loss matches the equivalent of a global ocean of water, spread a few tens of meters deep over the whole planet. And remember, this is the current rate, with today's relatively calm sun. Earlier in solar system history, the young sun was blasting out much more high-energy radiation, which drives escape even harder. When scientists look at isotope ratios, especially the ratio of heavy to light hydrogen and oxygen, they can see the fingerprint of this long-term loss. Lighter isotopes escape more easily, so the atmosphere and remaining water get enriched in the heavier ones. Matching those isotope signals to escape models suggests that at least around 10% of the hydrogen that started out as water on Mars has already been lost to space, and that's a lower bound. The real number is probably higher because past escape rates were stronger, so that brick per second number is not a curiosity, it's the tail end of a process that stripped a lot of water and air. So what is the air you'd actually be walking through if you step out onto Mars in a suit? Today, Mars' atmosphere is about 95% carbon dioxide. Roughly 2.7% is nitrogen, about 1.6% is argon, and everything else, oxygen, water vapor, trace gases, is in tiny fractions of a percent. The surface pressure averages around 6.3 millibars, which is more than a factor of 100 lower than Earth's mean sea level pressure of 1013 millibars. In lab terms, that's close to a vacuum experiment. In everyday terms, it's like being at an altitude way beyond the summit of Mount Everest. Your body cannot handle that. Without a pressurized suit, your blood and body fluids would start to boil, not because they're hot, but because the external pressure is too low to keep them liquid. That means your suit is not just there to give you oxygen, it's there to provide pressure. Your habitat has to be a controlled bubble that holds in a dense, Earth-like mix of nitrogen and oxygen at a pressure your lungs and blood vessels evolved for. The outside air is not something you can ever get used to. It's a hostile, almost vacuum-like environment made of mostly CO2, with just enough other stuff to matter for chemistry and climate, but nowhere near enough to matter for breathing. So how do we know this thin, harsh atmosphere used to be very different, and is still sliding downhill instead of sitting in balance? The escape rates we measure now, combined with isotope data and models of how the sun has changed over billions of years, point to a clear story. Early Mars had a thicker atmosphere, dense enough and warm enough at the surface for stable liquid water. That matches the old river valleys, lake beds and delta deposits we see carved into the crust. Back then, with more air and more greenhouse gases, water could stand on the surface as lakes and maybe shallow seas. But once the planet's internal magnetic dynamo weakened and the global magnetic field faded, the upper atmosphere became much more exposed to the solar wind and high-energy radiation. Over time, molecules in the upper atmosphere were broken apart, and the lighter fragments gained enough energy to escape Mars' gravity. Carbon dioxide can be lost directly and indirectly through this process. Water is broken into hydrogen and oxygen. Hydrogen escapes easily. Oxygen can recombine or also be lost. The result is a slow transformation from warm and wet to cold and dry that is not done yet. The atmosphere you see today is a shrinking remnant, not a stable end state. The numbers from MAVEN and other missions say clearly, the gas above Mars is still draining away. If you're thinking about terraforming, about turning Mars into something Earth-like, how does this ongoing leak change the picture? It makes things harder than the optimistic stories usually admit. Any plan to thicken the atmosphere by releasing CO2 from the polar caps and the soil, by importing gases with comets or asteroids, or by industrial production on the surface, has to fight against the same escape processes that strip the original atmosphere. You're not starting from zero with a calm environment. You're working against a permanent loss mechanism powered by the sun, and by the lack of a strong global magnetic field. In practice, that means two things. First, you'd need a way to build and maintain atmospheric pressure that is strong enough over long timescales to matter, not just a quick boost that leaks away over a few million years. Second, even if you succeed in the short term, you need continuous maintenance. You'd have to keep adding gas at some rate to balance what's still escaping. Without that, the planet will slowly drift back toward thin, cold and dry. Mars is not a static foundation you can modify once and forget about. It's more like a system with a built-in drain that never fully closes. And that raises the next key question. If the atmosphere is leaking now and used to be better protected, what went wrong inside the planet itself? What happened to Mars' magnetic shield? And what does its current cooling core tell you about where this world is headed next? How do you know Mars once had serious protection from space, when today it's basically standing naked in the solar wind. Right now, Mars has no strong global magnetic field like Earth's. A compass on the surface wouldn't calmly point north, it would twitch and point at weird local directions, or not give you anything useful at all. But when orbiters flew low over some regions, especially in the southern highlands, their instruments picked up strong patches of magnetized rock in the crust. These patches line up in patterns, strips and blobs where the iron minerals inside the rock are all pointing in similar directions, like frozen compasses. You only get that if those rocks cooled and solidified while a global magnetic field was active, and then that field switched off later. So the crust is carrying a ghost record of something Mars has lost, a past magnetosphere. That implies the core back then wasn't just hot, it were molten and convecting hard enough to power a dynamo, basically a self-sustaining magnetic engine. At some point early in the planet's history, that dynamo weakened or died. The crust kept its old alignment like a tape recording, while the field itself vanished. So why does that matter for anything beyond cool ancient magnetism trivia? On a planet scale, a magnetosphere is a shield. It deflects a big chunk of the charged particles streaming out from the sun, the solar wind. When you have that shield, most of those charged particles are forced to flow around your planet rather than slamming straight into the upper atmosphere. Lose the shield and the atmosphere becomes the front line. High energy particles and radiation slam into it directly, break molecules apart and give some of the fragments enough speed to escape the planet's gravity. That's a big part of why Mars is bleeding gas into space today. When the internal dynamo ended, it wasn't just some quiet internal change. It was a turning point for the whole system, climate included. A thicker atmosphere and any surface water that depended on that pressure suddenly became more vulnerable. Oceans and lakes could no longer be long-term stable. Any surface life that might have existed went from being under an umbrella to standing in a radiation storm. The climates slide from thicker, warmer and wetter to thin, cold and dry is tied directly to what happened in the core. The obvious follow-up is, if the global field is gone, is the core totally dead, or is something still going on down there? Seismic data from InSight combined with how Mars rotation wobbles and how gravity measurements behave point to a core that is still liquid, or at least partially liquid. The exact structure is still being refined, but you don't get the measured seismic wave speeds and attenuation if the whole core is solid iron. That means heat is still leaking out from the interior, and the mantle above the core is still convecting, just more gently than Earth's. That slow motion is probably what's driving things like the Mantle plume under Elysium Planitia, the volcanic region we talked about earlier. It's not enough organised, vigorous flow in the right pattern to reboot a strong global magnetic dynamo, but it is enough to generate stresses in the crust, cause marsquakes, and keep localised volcanism possible. So Mars isn't a burnt-out coal, it's more like an underpowered engine still turning over. The dynamo that once made a planet-wide magnetic shield has shut down, but the heat engine that moves rock and drives quakes hasn't stopped yet. That puts you in a middle situation, and it's easy to misread that. People hear no global field and think fully solid, fully dead inside. People hear liquid core and think, why no magnetic field then? The reality is a gradient. The energy budget dropped below the threshold needed to sustain a strong, ordered dynamo, but not to zero. So you end up with the internal motion that's enough to crack the crust and feed plumes, but not enough to build a big coherent field that reaches out and protects the atmosphere. Every marsquake you detect, every new crack around Cerberus Fossae, every hint that lava has erupted in the last few 100,000 years is a reminder that the interior is still cooling and adjusting. Think of the planet's interior as ticking forward, but on long intervals. A quake here, a slow uplift there, a tiny change in the gravity field as material shifts. The ticks are not seconds, they're thousands to millions of years apart for the big events, but they're still happening. The seismometer has already heard some of them. Orbiters have already seen their surface signatures. So what does that slow ticking actually mean for the future of Mars, not just its past? If the core keeps cooling and more of it solidifies, several things change. The rate at which heat escapes will gradually drop, which will affect how strongly the mantle can convect. If mantle convection weakens, volcanism slows further, and the crust's stress patterns change. That could mean fewer quakes over very long timescales, fewer new volcanic deposits, and less fresh gas being injected into the atmosphere from below. At the same time, the lack of a strong magnetosphere won't fix itself. As long as the dynamo stays off, the atmosphere will stay exposed to the solar wind. Escape rates might decline slowly as the remaining atmosphere shrinks and as the sun's output changes, but the direction is the same: loss, not gain. Water will keep being sequestered in ice in the crust and polar caps, and some fraction will keep being broken apart and lost to space. So you're catching Mars in a transitional state, not at a clean endpoint. It's past its most active volcanic, magnetically strong phase, but it hasn't frozen into a total geological fossil yet. Interior processes still shape the crust. The crust still moves, the atmosphere still evolves, and the climate still shifts. For you, that means this isn't just a world you study as a finished example. It's a system that's still changing under your feet and above your head, just slowly. Any plan to live there long term or to radically change the environment has to factor in that slow background evolution, not just today's snapshot. And that brings up one more disturbing loose end. If the core is still warm, the mantle is still moving, and gases are still seeping out, what do you make of the tiny flickering signals of methane in that thin air? Are they just chemistry in the rocks? Or are they a hint that something deeper, maybe even biological, is still active too? How do you ignore a planet that keeps leaking a gas we usually watch very closely on Earth because of life and industry? On Earth, methane is tied to biology in a big way. Microbes make it in swamps. Cows produce it in their guts. Humans pump it out from fossil fuel extraction and agriculture. So when Mars shows even tiny hints of methane in its ultra-thin air, you pay attention. Instruments like the tunable laser spectrometer on the Curiosity rover have detected methane in parts per billion levels. That's a few molecules of methane out of a billion molecules of air. Some analyses show a seasonal pattern, a bit more methane in certain parts of the Martian year, a bit less in others. Other instruments, especially from orbit, see weaker or no clear signals and argue the variations are smaller than first claimed. The data are messy, but they're not zero. There are at least occasional whiffs of methane in an atmosphere where that gas should not last long. The easy mistake here is to jump straight to methane equals life. But even if you rule life out completely, methane still forces you to accept that something underground is active. There are several non-biological ways to make methane. One is water-rock reactions, like serpentinization. In that process, certain minerals in the crust react with water and produce hydrogen, which can then react with carbon-bearing compounds to make methane. Another option is that methane was produced long ago, by biology or geology, got trapped in subsurface ice or in special structures called clathrates, and is now leaking out slowly through cracks. All of those processes need energy and fluids. You need liquid water or brine moving through rock. You need heat to drive reactions. You need fractures and pores to move gas around. So even in the most conservative, the no life at all scenario, methane on Mars is a sign of an interior that's doing chemistry, not sitting inert. Fresh rock is being exposed, water or brine is contacting it, and gas is moving from depth to the surface. That's already a very different picture from a cold, perfectly dead rock. What makes this even more interesting is that the methane doesn't seem to just sit at one level and stay there. Measurements hint at day-night and seasonal differences. Some readings show higher methane near the surface at night, dropping during the day. That suggests methane might build up close to the ground when the air is calm and temperatures are low, then get mixed and diluted when daytime heating stirs the atmosphere. Sunlight, especially ultraviolet, can also break methane apart, so daytime is when destruction is most efficient. On top of that, there may be seasonal trends, with methane levels being slightly higher in certain parts of the Martian year and lower in others, possibly linked to temperature, pressure changes from the polar CO2 cycle, or how brines and subsurface gas reservoirs behave. The details are still being argued about, but the pattern is clear enough to matter. Methane is not constant. That means the processes that create, trap and destroy it are operating on timescales of hours, days and months, not just on million-year cycles. So does that mean Mars has life? No. Not on methane alone. That's the hard line you have to hold. On Earth, methane is often a biosignature because biology is so dominant in making it. On Mars, geology could easily be responsible, or at least a big part of the story. You can't point at a parts per billion signal in a thin, noisy atmosphere and declare microbes. You'd need to rule out all reasonable geologic sources, look at isotope ratios, and see other signs of metabolism before you could seriously claim biology. We're nowhere near that yet. But here's the part people sometimes gloss over. Even if you prove every methane molecule is a biotic, the implications are still big. Geological methane is not a passive feature. It means water, or brine, is interacting with rock. It means the crust has usable chemical gradients, places where reduced and oxidized compounds meet and can react. It means there are subsurface pockets where fluids are moving and heat is doing work. Those are exactly the environments where, on Earth, microbes set up shop and stay there for billions of years. So every time you find a plausible non-biological way to make methane, you're also describing a potential habitat. From an engineering and mission planning point of view, the methane puzzle also tells you something about timescales. In a thin CO2-dominated atmosphere blasted by ultraviolet light, methane doesn't last very long. Rough numbers put its lifetime on the order of a few hundred years or less. In some scenarios, with active oxidation at the surface, it could be much shorter. That means if you can detect methane today, it has to be replenished. You can't just be seeing the leftovers from some event a billion years ago. The source has to be operating, at least occasionally, in the present era. So whatever is feeding the methane signal, life or geology or both, is another ongoing cycle layered on top of the quakes, dunes, frost, and escaping air. Mars is not just cooling and cracking, it's also reacting chemically underground and in the lower atmosphere, turning rock, water and gas into new combinations. For future missions, this is a clear challenge and an opportunity. If you send a lander or rover to study methane properly, you need instruments that can measure incredibly low concentrations with high accuracy and can tie those numbers to specific times of day and year. You want to know if spikes are tied to specific locations, like faults or old volcanic regions, or if they're more spread out. You want to track how quickly methane disappears, which tells you how aggressive the destruction processes are. You want to know if those processes are purely photochemical, or if the soil and dust are actively grabbing methane and breaking it down. All of that demands more hardware on the ground and in orbit. More spectrometers, more weather stations, more long-lived rovers parked in the right places. And for any human presence, methane is another piece of the environmental puzzle. It tells you something about the gases you might encounter near the surface, the chemistry happening in the soil, and the possible risks or benefits of tapping subsurface fluids. The key point, again, is that nothing about methane fits a truly static Mars. A gas that gets destroyed in hundreds of years but is still present in a parts per billion atmosphere must be getting topped up somehow. That somehow is an active process, not a fossil one. And if even a fragile gas like methane can keep cycling in a thin, oxidizing, UV-bathed atmosphere, that leads straight to the next question. What else are the salts, brines, and reactive chemicals in the Martian soil doing right now, in the shadows and pores of the surface, to keep this planet's chemistry on the edge instead of letting it shut down? How do you call a planet dry and dead when its soil is packed with chemicals that grab water and refuse to let it behave normally? Across Mars, spectrometers on landers and orbiters have found sulfates, chlorides, and especially perchlorates in the dust and rocks. These are salts, and they don't just sit there doing nothing. They hold on to water molecules and drag down the freezing point. On Earth, you use salt on roads to keep ice from forming as easily. On Mars, the effect is even more extreme. A brine loaded with perchlorates can stay liquid down to around minus 70 degrees Celsius, about minus 94 degrees Fahrenheit, if the pressure and humidity line up. Those conditions do happen near the surface at certain times of day and year, so even in an environment where pure liquid water is unstable, salty water has a window where it can exist. The next question is, does that ever actually happen in a way that matters, or is it just theory? Under today's low pressure, you're not going to get a big stable lake on the surface that's basically ruled out. But you don't need a lake for interesting things to happen. Thin films or tiny droplets of brine could form in the subsurface in cracks, or in the spaces between grains of soil. The most likely times are when temperatures are changing quickly, like around dawn and dusk. At those times, frost can form and vanish, humidity near the ground can spike and drop, and salts can briefly pick up enough water to form a liquid phase. These films might last minutes to hours before they evaporate or freeze again. To you, that sounds like nothing. You blink and they're gone. To a microbe adapted to that pattern, that could be enough. On Earth, there are organisms that wake up when moisture appears, do a burst of metabolism, then go dormant again when conditions dry. The point isn't that this is definitely happening on Mars right now. The point is that the chemistry and physics don't rule it out. The salts make it possible in a way a pure ice, pure rock world wouldn't. Salts also change more than just whether water is liquid. They change how the ground behaves as a material. Hydrated salts, salts that have taken up water, can swell, shrink, and soften or stiffen soil. As they gain or lose water with temperature and humidity changes, they can expand and contract. That can help break grains apart, weaken bonds between particles, and lower the friction that holds slopes in place. When that happens on a steep slope, even a small extra push, a gust of wind, a tiny frost cycle, a marsquake, can tip the balance and start a flow. Some behaviour you see in recurring slope lineae and other streaks may be exactly this. Salt-rich regolith changing its mechanical properties with small environmental shifts and then sliding down slope. Not a nice clear stream of liquid, but a kind of slow granular flow where grains lubricated by brines or softened salts move as a unit. That's chemistry directly feeding into geomorphology, the shape of the land, right now, so you have salts that can make brines and push soil around, but they come with a big downside if you're thinking about life or organics near the surface. Perchlorates and other oxidants are chemically aggressive. Combine them with intense ultraviolet radiation from the sun, which slams into the surface because there's almost no ozone layer or thick atmosphere to stop it, and you get a tough environment for complex organic molecules. UV light breaks bonds in organics. Oxidants then react with the broken fragments, turning them into simpler, more oxidized products like carbon dioxide. That means any complex organic molecules sitting near the surface, whether delivered by meteorites or produced in the past, can be destroyed on relatively short timescales. That's bad news if you're hoping for surface life strolling around unprotected. It also makes life detection harder, because the top layer of soil is constantly being cleaned of organics. But from the standpoint of planetary activity, it's clear evidence that chemistry is ongoing. These reactions are not fossils. UV is hitting the ground every day, oxidants are reacting every day, new dust and salts are being exposed every day. The surface is chemically hostile and chemically busy at the same time. When you put all of this together, you get a picture that doesn't match chemically dead at all. You have salts cycling water between solid, adsorbed, and liquid brine phases. You have hydrated minerals swelling and shrinking, helping slopes fail and soil creep. You have oxidants and UV radiation constantly attacking organics. You have thin films of brine that might form and vanish in the subsurface, briefly making tiny environments that are wetter and more chemically rich than the average surface. Mars is not a place where chemistry did something interesting billions of years ago and then froze in place. It is a place where chemistry is still running in small, harsh, repetitive cycles. It's a cold, salty lab bench that keeps doing experiments every day, using energy from sunlight, from temperature swings, and from the slow release of heat and gases from below. For you, this means two things at once. First, as someone interested in life, it tells you where to look and what to protect. Subsurface zones with salts and occasional brines are higher value targets for habitability than bone-dry, salt-free rock. Second, As someone who might live there, it tells you what you're building on and breathing around. The soil can change its strength as salts hydrate and dehydrate, and the dust is loaded with oxidants that you do not want inside your lungs or your machinery. And that sets up the real tension for the last part of this story. If Mars is geologically active, chemically restless, and maybe even capable of brief liquid pockets underground, what does that actually mean for life? Both any microbes that might exist there, and you trying to survive on top of a planet that is alive in all the ways that make things harder. If Mars is this active and this harsh, does that make it a better place for life, or does it just make it more dangerous for you? On Earth, life shows up wherever there's a difference it can exploit: hot versus cold, acidic versus neutral, oxidized versus reduced, wet versus dry. Microbes don't care about pretty views, they care about energy gradients. Mars, even today, is full of those. Volcanic heat in places like Elysium Planitia, water-rock reactions that can make gases like hydrogen and methane, ice that moves and deforms, an atmosphere that's literally leaking into space and changing as it goes. All of that creates chemical and thermal contrasts. You have warm rock next to cold ice, reduced minerals next to oxidized dust, salty brines next to dry soil. Even if the surface is brutal with radiation and oxidants and extreme cold, the subsurface could still offer pockets where energy and water stick around long enough for something small and tough to use them. So if you were a microbe on Mars, where would you actually hide? You wouldn't sit on the surface in plain view. You would go a few meters down or more where radiation drops off and temperatures are less extreme. Near Cerberus Fossae, you could sit in fractures where magma once rose toward the surface. Those rocks might now be warm, not molten, shot through with cracks full of gases and maybe brines. That's a steady heat sound source and a source of chemical energy. Under debris-covered glaciers in the mid-latitudes, pressure at the base plus a little geothermal heat might occasionally make tiny amounts of meltwater, just enough to wet grains and let ions move. Those are exactly the types of niches extremophiles use on Earth, deep in rock, under ice, inside volcanic systems, where light hardly matters and chemistry runs the show. As ongoing dynamics make these places more likely, not less. Quakes keep opening and reopening pathways. Volcanic regions keep concentrating heat. Ice keeps shifting and responding to climate cycles. If life ever got started there, even at a very basic microbial level, these changing subsurface environments are the kind of refuges where it could hold on for very long periods, long after the surface became hostile. And if such microbes existed, what would they eat? They definitely wouldn't be picking fruit off trees. Their food would be rock, gas and ions. Quakes crack rock and expose fresh mineral surfaces that haven't been fully oxidized. Landslides strip off weathered layers and reveal new material. Dunes grind grains against each other, constantly producing fresh surfaces. Each of those processes is like grinding a new batch of reactive minerals for chemotrophic microbes, organisms that get energy from chemical reactions rather than sunlight. Iron-bearing minerals, sulfur-bearing minerals, reduced carbon trapped in the crust, all of these are potential energy sources if you pair them with the right oxidants. Mars supplies oxidants too in the form of perch laurets and other reactive compounds in the soil. So even without sunlight, a deep biosphere could, in theory, run off the planet's slow grinding geology. Every marsquake, every slope failure, every dust storm that sands down a rock is another small input of fresh fuel into that system. Now flip perspective. You're not a microbe trying to survive 1 billion years. You're a human team trying to survive a mission. How does this living Mars help you, and how does it try to kill you? The same geology that supports potential habitats also gives you resources. Ice in buried glaciers and mid-latitude deposits is your water source, your oxygen source, your hydrogen for fuel. Volcanic regions concentrate useful minerals and may offer geothermal gradients you can tap for power or heat so you don't rely only on solar or nuclear. Active processes that keep exposing fresh rock make it easier to find interesting ores and hydrated minerals without drilling kilometers deep. But there's a price. Marsquakes mean the ground can move under your structures. You design bases with flexible supports, low centers of gravity, and margins that assume periodic shaking. Gullies, RSL, and frequent slope streaks mean some cliffs and crater rims are unstable today, not just in theory. You respect them and map them and keep your main habitat away from their run-out zones. Moving dunes and dust storms mean the terrain and the sky over your infrastructure will not stay constant. Sand can bury cables, ramps and landing markers, and dust can cut your solar power for weeks or months. On top of that, long-term trends matter. Over decades, shifts in where ice sits near the surface, or how often big dust storms occur, can change where it's practical to operate. You're not planting a base in a museum exhibit where nothing changes. You're moving into a house that's still quietly settling, with pipes shifting in the walls and the roof flexing in every storm. If you design as if Mars is dead, you will be surprised in all the worst ways. So why should you be glad Mars is like this, instead of some totally frozen, totally inert rock? Because a truly dead planet is boring scientifically and practically. If there were no quakes, no moving dunes, no changing streaks, no breathing polar caps, you'd get a nice clean fossil record and not much else. There would be almost no new information flowing in. You'd have fewer clues about the interior, fewer active gradients, and less reason to believe any subsurface biosphere could still be hanging on. You would also have fewer resources being naturally concentrated or refreshed by ongoing processes. Instead, you have a planet that still rewrites parts of its own surface. The handwriting is slow and thin, but it's there. Quakes tick in the background. Volcanic regions refuse to shut down completely. Ice moves and records climate swings. The atmosphere breathes storms and leaks into space. Salts and brines keep chemistry on edge rather than letting it freeze into a single simple pattern. For life, that means energy and niches. For you, that means a mix of opportunity and risk that doesn't go away just because you planted a flag. You're not just exploring a past world, you're trying to live on a present one that is still evolving. And that leads to the last step in this whole argument. If Mars is still shaking, creeping, breathing and leaking, then the real question isn't is it dead or alive, it's how fast is it changing and how do you live on a planet whose heartbeat is slow but definitely still there? How do you confuse slow with dead just because a planet doesn't move on your schedule? You're used to Earth's pace. Volcanoes that can erupt within a human lifetime. Earthquakes that go from silence to violent shaking in a few seconds. Storms that spin up in a day and vanish a week later. Your sense of alive is locked to that speed. Mars runs the same kinds of processes, but on a slower setting. Volcanic deposits that are tens of thousands of years old instead of centuries, quakes that happen a few times a month instead of hundreds a day, dunes that creep by a meter over a couple of years instead of meters in a stormy season. Slower, yes. Dead, no. A planet doesn't stop being active just because its main moves happen on a scale that spans generations instead of news cycles. So if you want one clear way to think about modern Mars, how do you break it down without getting lost in all the details? Think in terms of 4 heartbeats running at different speeds all at once. First, there's the seismic heartbeat. That's the marsquakes, coming from deep faults and probably from active mantle plumes like the one under Elysium Planitia. InSight has already picked up hundreds of quakes. Some are small, some are strong enough to rattle boulders. Each one is the crust adjusting to stress from below, proof the interior is still cooling and moving. Second, there's the surface heartbeat. That's dunes shifting, gullies refreshing, slope streaks appearing and fading, landslides carving fresh scars. You see the changes in before and after orbital images. A dune crest here moves by about a meter over a Martian year, roughly 1.9 Earth years. A new bright gully deposit shows up between images. A fresh dark streak cuts down a slope that was clean in the last pass. Those are yearly to decadal ticks, the surface telling you it's still in play. Third, there's the cryo heartbeat, the ice cycle. Each Martian year, up to about a third of the CO2 atmosphere freezes out as dry ice at the winter pole, then sublimates back into gas in spring and migrates to the other pole. That makes surface pressure swing by roughly 25 to 30% globally. The polar caps grow, retreat, and push frost down slopes that can slide and destabilize material. That's a planet-scale breath, in and out on a 1 Martian year rhythm. Fourth, There's the atmospheric heartbeat. Dust storms that can stay local or expand to wrap the whole globe. Tiny methane signals that rise and fall with time of day and maybe with the seasons. A steady outflow of hydrogen and oxygen to space at a rate of a few kilograms per second. The air is not just sitting there. It's circulating, storming, reacting and bleeding away into the void. You put those four together and you don't get a corpse. You get a slow, low-frequency system that just happens to run on a clock much longer than yours. So why does this wreck the old empty wasteland picture you grew up with? For a long time we only had fuzzy images and basic data. Mars looked like a dry desert with old riverbeds and craters, and no obvious eruptions or quakes in human memory. It was easy to say, okay, cool fossil, but the action stopped billions of years ago. That story fit what we knew then. Once we landed seismometers on the ground and started building decade-long time-lapse movies from orbit, that story stopped fitting. Now you have direct measurements of quakes. You have crater count dating that tells you some volcanic deposits are only tens of thousands of years old. You have repeated imaging that shows dunes migrating and new streaks and slides forming. You have pressure records showing the atmosphere rising and falling as the poles freeze and thaw. You have escape rate data showing gas is still leaving for space right now. The only way to keep calling Mars dead is to ignore a huge amount of hard data, so the Mars you should be carrying in your head now is not the postcard from school. When you look up at that red dot, don't picture a static ball of rust. Picture a crust that still flexes and cracks, sending seismic waves through a warm mantle and a partially liquid core. Picture dunes tens of meters high, tens of yards high, walking slowly across crater floors and polar plains. Picture polar caps that don't just sit there but literally grab a big chunk of the atmosphere every winter and then release it. Picture an atmosphere that is thin but active, with storms that can darken the whole sky and with molecules like methane still being added and destroyed. And over all of that, picture a slow leak of gas into space, an atmosphere that is still shrinking, not finished. You're alive at the time when we finally have the instruments and the time baseline to see this clearly. 100 years ago, Mars was just a blurry circle with some dark patches. 50 years ago, it was probably dry and dead. Now it's a world where every new mission discovers another piece of motion, a new quake, a new slide, a new deposit, a new twist in the gas. So here's the straight conclusion, no soft edges. Mars is not what you think. It's not a static wasteland. It's a slow, low-frequency, geologically and chemically active planet in the middle of a very long transformation from thick, warm and wet to thin, cold and dreary. The pace is slow compared to Earth, but the processes are the same categories: quakes, volcanism, erosion, climate cycles, atmospheric loss. If you ever stand there in a pressurized suit, your radio will pick up the faint thump of a marsquake through a local seismometer, the slow gusts of dust-laden wind hitting your habitat, the hiss of sand bouncing against your rover. None of that happens on a true corpse. If you step onto Mars, you are not stepping onto a dead rock that finished its story billions of years ago. You're stepping onto a world that's still writing the next chapter, just in a handwriting so slow you needed robots, orbiters, and careful measurements to notice. This video's for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.